Okay, so for our next speaker, let me introduce Professor Amit Kumar. He's from IIT Delhi. He's the Jaswinder and Tarvinder Chadda Chair Professor there. And his research lies in the areas of combinatorial optimization and online algorithms. Today, he's going to be talking on facility location. Just two other things that I need to announce. One is that we'll be doing the photo session tomorrow, right before the Ask Me Anything session with the faculty. And also, please carry this ID for whenever you're going to the lawn for food, because we have been noticing some people who are not registered there. So yeah, that's it. Thank you.
Okay, so can you hear me? Alright, so I work in the area of approximation algorithms, online algorithms, so that is what I will talk about. Today I'm going to tell you about facility location. Now facility location is a very large area. People start by defining what the problem is, because we don't have much time. So, and feel free to stop and if you don't understand something, because I'm going to assume that you know what a linear program is. You've seen that, you know how to write a dual, but maybe not enough about it. And you know some basic NP-complete problems. You know what set cover, vertex cover, those kind of things. So okay, what is the facility location problem? As the name suggests, there are two sets. Okay, so there are two sets. One is let's call it the set of facilities. And so imagine that you want to open some shops or some warehouses, and so this set F is telling you what are the possible locations at which you can open the shop. So of course you want to optimize something. You don't want to open a shop everywhere because there is a cost associated with opening a shop at any point. Okay, so the input is for every point I in F, I'm going to give you a number which is, let's call it Fi, which is the facility opening cost. So if you open a facility there, you will pay this facility opening cost. Okay, so that's the facility side. Can you read this? Big enough for you? Not big enough? Bigger? Yeah. Okay, so at location I. Alright, so that's one side. The other side is what is called the demand or the client. So I'm going to call it D. So D is the set of demands. So these are the people living in the neighborhood who are going to go to these facilities. So if you open some shops or hospitals, so these are the people who are going to go and get service there. Okay, so this is another set here. So these are called demands. So let's say I open a facility here, I open a facility here, maybe another one here. And what you are also given is you are given distances between them. Okay, so right, so there is a set of facility F, each has an opening cost, set D, and then for every, so I'm going to consistently use I for a facility and J for a demand. Okay, throughout. So Cij tells you what is the distance between J and I. So you're also given these numbers, Cij. Okay, so Cij is the distance between demand J and facility I. And then you want to, if you open these three facilities, where do you think a particular demand should go to? What is the nearest one? The closest one. So everybody goes to the nearest one. Okay, and so you also want to make sure that people don't travel too much. Okay, so you want to minimize what is called the total opening cost plus the total travel cost. Okay, so you want to minimize, right? So summation Fi for all those facilities which are open, right? So open facilities, right? And let's call this set something. So let's call this set O. Right, so O is the set of facilities that you're opening. So I'll just write it as I in O. Okay. And the the distances these demands have to travel. Right? So plus sum over all demand j. Well, how much distance will I travel? Well, I'll travel c of the minimum one. Right? So let's call this ij, comma j. What is ij? Ij is the nearest facility. Right? So ij is min I in O C I J. Okay, and these two are not say in the same currency, so I'll just put some maybe some sort of scaling factor here, right? So that they are in the same currency, but that scaling factor I'm going to absorb in C, so I'm just going to think of this as this. So far so good. Okay, so as such, I want to claim that so this is a facility location problem. You want to balance between these two things. You don't want to open too many things. If you open too many things, this goes down, but then this goes up. If you do less here, then this goes up. Now, as such, I want to claim that this is at least as difficult as the set cover problem. Okay, so and set cover, what is the best approximation we know? What is the approximation that we know for set cover problem? Greedy algorithm. Log n, right? Log n. So what that would mean is that the best you can hope for here is log n, if I just don't impose anything else on this. Okay. So let me show you that, and that's not very optimistic because in real life settings there will be more conditions, and you will perhaps suggest. But let me show you why set cover can be thought of as facility location. Okay. So set cover, I want to give a reduction to facility location. Okay, so far so good. What is set cover? Remember, set cover, you are given some set of elements u, and you are given a bunch of collection of subsets of u, right? Let's say m, which are subsets of u. And what is your goal? Your goal is to pick a sub collection here whose union is u, and you want to minimize the number of such sets. Okay. So what is the reduction? Right? How will I do this reduction? So what do I want to do? Remember, I want to take this problem and I want to pose it as a facility location problem. And I want to say that if you can solve facility location, then you can get a solution here also. Right? In fact, if you get any approximation here, you will get the same approximation here. Okay. So again, it's very simple. So it says that for the set of facilities, well, here what is the decision you have to make? Decision you have to make is which sets to pick. So what do you think should be my facilities? Maybe one for each set, 1 point for every set, right? So 1 point for every set, right? So each I here corresponds to, let's say, the set Si. Okay? So that would be my set of facilities. What do you think should be the set of demands? Well, U, what else, right? So set of all U. So this is essentially same as U. So far so good. What should be my facility opening cost? I put all facility opening cost as 1 because here you are minimizing the number of sets. Here I want to minimize the cost of the facilities. So I'm going to set each Fi to 1. Okay? So each Fi is equal to 1. So very simple, right? Now it remains to figure out what are the distances. So far I have not used the structure of the set system at all. Right? Which element is contained in which set, I have not used that fact at all. So how should I do that? Remember, I have to specify a distance between every pair of points. And again, that is done in a very natural way, right? So it will say that if a point j is contained in the set Si, I'm going to draw, so this distance I'm going to make it 0, otherwise I'll make it infinity. Okay? So, alright, so Cij is 0 if the point j is in the set Si, otherwise it's infinity. Okay? So if you're not in that set, you're infinity. What that means is that for every point here, you must open a set here which contains that point. Otherwise you're going to pay infinite cost. So what is the solution here? Well, connection cost will be 0. Because it's either 0 or infinity, you cannot pay infinity. So whatever you do, connection cost has to be 0. So which means that whatever facilities you open here, that will act like a set cover. So this is exactly set cover problem. Okay, so any approximation here, anything you do here translates the same thing here. So that means that there is no hope, right? I mean, even if, yeah.
So just a sanity check. So each facility meets only certain demands?
No, each facility can serve anybody. So I will specify a distance from I to everybody else. And what is that distance? If this point is in this set, I will set that distance to 0, otherwise I will set it to infinity.
But potentially every facility can meet every demand.
Any facility can serve any port. No restrictions on that. Okay. Now, right, so that's pessimistic, but then you will realize that maybe this is not so realistic. What do you think is unrealistic about this kind of facility location instance? Something which will not be normally true in real life settings. Yeah, so you can't have infinite distance, you can't have zero distance, but more importantly, what you could have here is that, for example, what could happen is that this may not satisfy. Let's say, for example, it's possible that this is 0, but this is infinity. This kind of thing is possible, right? Because, right, I mean, this element can be present in this set and this set. So this element is not present in this set, but it is present in both these guys are present here, right? So depending on how it behaves, you could have a situation like this, which does not make sense, right? It says that all these 3 are 0 distance, this is 0 distance here, but this is infinity. So it violates what is called the metric property, triangle inequality, right? So I'm going to add that extra condition now, right? So if you don't have this metric condition, then we know that this is at least as hard as set cover. Now what you will do as an exercise, which I am giving as an exercise after you have seen everything here, you will be able to prove that even for this facility location problem, where you don't make any assumptions, you can still get a log n approximation, right? So exercise for you, which you will not be able to do right now, but after you have seen. So give a log n approximation algorithm for facility function. Okay. So what I'm going to do now is I'm going to modify the problem and I'm going to put a metric here. Okay. So what that means is that all of these points, they live in a metric space. So now we have a distance between every pair of points, but these distances are going to satisfy triangle inequality. Okay. So that's the extra thing I have. Okay. So I'm just going to keep everything unchanged, but the only change which happens is that if you give me these guys live now, F and D, all of them live in some metric space, which means that the distance, they satisfy triangle equality. If you give me 3 points A, B, C, then the distance between A and C is less than or equal to distance between A and B plus distance between D and C. Okay, so this is called triangle inequality, and I'm going to assume that they satisfy this triangle equality. And it's natural, right? If points are in the plane, in any 3D space, you know that that's how it will be. But in any other scenario also, if you're given a graph and this distance is the shortest path distance between those 2 points, then I also know that this property is satisfied. Okay? So let me write it down, make it x, y, z. Okay, let me make it a1 into a3. So what I'm assuming is that C a1 a3, distance between a1 a3, okay, always. So they satisfy the triangle equality. Now the question is, can I do better than log n? Can I give, for example, a constant approximation for this problem? So this is what I want to show you, and the idea is not to give a constant only, but also show you that there is a variety of techniques here. So depending on how much time we have, I'll show you 2-3 different ideas which are present here. Okay? Alright. So you have already seen that if you want to solve a combinatorial optimization problem, a good starting point is to write a linear programming relaxation for it. So that's where I'm going to start with. I'm going to write a linear program for this, okay, and hopefully it is straightforward enough that you will be able to see why that is a valid linear program, and then I'll show you how to route it.
The other direction study, like set cover where there's some sort of metric in the containments.
Sorry.
So like, yeah, it's a random question, but like the set cover problem, but I assume that the containments are such that I get a metric.
You get a metric, then of course you will be able to.
Okay.
Yes. Okay. So I'm going to write a linear programming relaxation, and I'm going to tell you what the variables are. Okay. So remember, I is for facility and J is for demand, right? So I is for always. So I have two decision variables. Both will be either 0 or 1. So yi is going to be 1 if facility is open, 0 if it is not. So it's an indicator variable. So it's meant to be 0 or 1 depending on whether I is open or not. On whether facility I is open. Okay, so if yi is 1, it means you are open, 0 means you are not open. That's one variable. And the other variable is assignment, xij, which is 1 if j is going to facility I. Okay, so is 1 if j is assigned to facility I. Assigned means it goes to facility I, 0 otherwise. Okay, so I could write it more clearly. 1 if it is open, 0 otherwise. This is 1. This is what it's supposed to be. So when you write a linear program, what do? You first think of it as an integer program where variables are either 0 or 1, and then you say that this I cannot solve, so I am going to make it into a linear program. Okay, so I am just writing it as an integer program. So far so good. So can I write this objective function? Now I don't know what O is, right? I mean that's what I am trying to find. So can I write this objective function in terms of xij and yi? How do you think I should do that? Well, if I is open, then yi is going to be 1, otherwise it's going to be 0. So I want to say that you don't have to put any O here. I can write it as sum over all I fi yi. Make sense? What do you think I should do here? Okay, so Cij, if Xij is 1, you pay Cij, otherwise you pay 0. So again, I can say that sum over all I Cij Xij. Right, this is the connection cost of I because I am only going to go to one facility. Okay, now what conditions should yi and xij satisfy? Well, first condition is that if I am going to go somewhere, this guy better be open. So if xij is 1, then yi should be 1 as well. Right? So xij is less than or equal to yi. What else? Sorry? What has not been captured so far?
Summation xij. Like J is assigned to only one of.
J is not only, in fact it's saying that J, I mean if you're trying to minimize this, what will you do? You will not assign J to anyone, right? So how do I say that you have to assign this J, right? So I'll say that if you sum over all facilities I, xij, you better assign this guy somewhere, at least one. Now if you assign two different guys, you're only overestimating, right? Overpaying, that you will never do. Right? That's why I don't have to say yi is less than or equal to 1, because it won't happen. And so they are non-negative, right? So that is the integer program, and you can make it linear program by saying that now let them be fractional, right? Let them be 0.2, 0.3, whatever they are. Okay. So this becomes the linear programming relaxation for facility location problem. Everybody with me so far? Why is it a relaxation? What does relaxation mean? Relaxation means that if you knew what the optimal value here was, right? So suppose you knew that this is your instance and this is the optimal value for the original problem. Where do you think is the optimal value of this linear program going to be? More than this or less than this? Less than this, right? It's clear? So the optimal value of LP will be less than this. Okay? Why? Because it's minimizing something, and if you give me any solution, integer solution, I can plug that in here, those yi's as 1, xi's as 0, 1, and this quantity will be exactly this value here. But I am minimizing and I am allowing my variables to be fractions also. So they could have. And what is the idea of rounding? The idea of rounding is that if you give me, this is something I can find, this is something I can solve, this is something I could not solve. But now I am going to give, if you give me an optimal solution here, I will now show you that how I can get an integer solution such that these two are close, right? These two are close. And because the actual optimum is going to be sandwiched between the two, I know that even this distance is small, right? So my goal is to prove that these two are close to each other. But how do I prove that? Because I don't know what opt is. And this is what linear program is doing for me, right? It's giving me a lower bound. So if you give me a solution for this, and I'm able to round it to some other integer solution, and I show that this gap is small, then it implies the same for actual opt. Okay? So that is the strategy. So now in the next half an hour, I'm going to show you two different rounding techniques. Right? One is direct rounding. The other uses duality, and the reason why I'm going to use dual is because it just motivates dual for you, and then we'll see how it goes. Okay? Questions? Everybody happy with this formulation here? Okay. So let me show you the most basic one first. Okay, so let's say you solve this linear program and you get a solution. Okay, so and just to make sure that it's an optimal solution, I'm just going to put a star here. So x star y star is optimal solution to that linear program, whose value is exactly equal to this. Okay. Now I want to open some facilities. Okay, how do I open these facilities? So for example, what could happen is that this is a demand, remember J is for demand, and there are various facilities, right? So there are facilities around it. Okay? So these are all the facilities around it, and the linear program would have said that to this facility I1 you give 0.1, to this one you give 0.2, to this one you give 0.1, and so on. Okay? And I have to figure out which one to open. Right? I know that if I add up all these fractions, what will I get? I'll get 1. Why? Because of this condition. Will it be more than 1? It could be more than 1, but what's the point of having it more than 1? Right? You are minimizing this. It will be exactly 1. Okay. So what do I do? Now, can I just say that open anybody and just let this go there? Well, what if this guy is very, very far? Right? Maybe I put a very tiny amount here, 0.001. Right? Maybe this was like 0.0001. Right? And this is very far. So if it is very far, but this quantity is very small, this product is not very big. So as such, this is not a very big number. But if you say that I'm going to send it right all the way there, then that will be too much distance. Okay? So first of all, this rounding algorithm, what it will do is it will kind of filter out these things. It will say that let's remove such nonsense guys. Okay? Once you remove these nonsense guys, what will happen is that anybody that you can send to will not be too far away. Okay? So far so good? So this is called filtering. So there are two steps. One is filtering and the other is called clustering. And I will show you both these steps. Because if you read a paper very often, you will see this word filtering. It's very commonly used in many other settings. So not only just this, but many other settings. Okay, so what happens here? So how much is the actual travel cost? Remember, what is this linear program saying? This linear program is saying that this demand J is going to go to all of these places fractionally. It was supposed to go to just one point, but now I'm sending it fractionally to everywhere. So what is the cost it's actually paying? So let's call that the fractional cost of J, right? Fractional cost of J, if you think about it, is the weighted distances here, right? So it is exactly this quantity. This I'm calling as Cj. Okay, so this is sum over all I xij star Cij. They're saying that this fraction times this distance plus this fraction times this distance, so on. Okay, so this is what the linear program is paying. Now what I will do is I want to look at a ball here. Okay, so I want to look at a ball of twice that radius. Okay, so I want to look at a ball of twice that radius. So this is, what does that mean? So, okay, I want to look at all those facilities, right, whose distance from J is less than or equal to 2 Cj star. Okay, and I want to say that I just want to restrict to this. Okay, I just only want to look at these guys here. Okay, now what does that mean? First of all, what I want to prove is that if you look at twice the radius from J, there are enough open facilities here. So I'll prove to you that if you look at there will be some facilities inside, and if you add up their yi values, remember all these fractions add up to 1. But if you only look at this inner ball, these fractions will add up to at least half. And the reason is like this, right? So suppose in a class, everybody gives an exam. Let's say the average marks is 30. If average is 30, it means that at least half the students are at most 60. Why? Because if half the guys were above 60, then the average would not be 30. Right? So that's the kind of argument this is. It's saying that if more than half of my assignment was going outside, then this sum would be at least half times 2 Cj star, which will be bigger than Cj star. So that cannot happen. Okay, so right, so inside this ball, right, so let's if you want me to define more formally, Bj star is a set of all I where Cij is less than or equal to 2 Cj star. And what it is saying is that at least half of the probability, half of the Yj is sitting here. So you can open anybody there, I will only have to go 2 Cj star. Okay? So I can actually do this upfront. I can change my solution where what I will do is I will erase all of these things which are going outside and double up everything inside. Okay? So what I will do is, right, first step, double all yi, okay, and I define a new solution x star ij, let's say x bar I star, which is twice of the original one if I is in that ball, 0 otherwise. Okay, so let's erase this. Okay, so what I have done is I have said that look, you wanted to send 1, so I am going to erase all of these guys and just double up my contribution here so that it adds up to 1, or it will add up to more than 1, right? Maybe more than 1. Okay. So that's good. So now what's the advantage of this? The advantage of this is that whoever I am going to get, I am getting fractionally assigned to, I can just open that facility and go there. It's not too far away. Nobody is too far away now. Okay, so that's the first step. If you have a doubt, ask now.
What if the xij exceed yi?
They will not exceed y, right? It is given to you, right? And I am doubling this and I am doubling this. So this condition is not violated. So let's see, a good point. So I am doubling these yi's. And what am I doing? I am zeroing some of them out and doubling the rest. So this condition is not going to be get by. It's still going to satisfy all of these conditions. Okay? The summation xij here will be at least half. So when you double it, it will become at least 1. So I have a new solution where all of these conditions are satisfied. Yeah, good, good. Okay, good. So what happens now? So now comes the second part, which is again very standard now, but it's again a very neat idea. So the idea is that.
So far you haven't used the metric property.
Sorry?
So far you haven't used the metric property.
So far I have not used the metric property. Nothing about this I could have done even in the earlier paper. Right. Where is the metric property? Right. So now let's pick. So now comes the actual rounding error. This was just as I know initial step to ensure that nobody is very far away from J. So now what will I do? I'll for a J whose Cj is very small, that is a small ball, right? So I'll pick a J. So now I'll go through several iterations. So I'll say what to do. So choose a demand with the smallest CJ value.
Why did we double all yi?
Why did we double? Okay, good. So remember what did we say? I went a little fast over this. So when you draw a ball of radius 2 CJ star, okay, and if you see how much of j is assigned inside, all I'm saying is that it should be at least a half. Why? Because if it were half outside, then sum of xij cij, right, will be at least 2 cj star times half, which will be more than cj star. That cannot happen because that's the definition of cj star. So more than half of j is going inside, but I want 1 of j to go inside. So if I double it, then I am sure that at least 1 of j goes inside. That's why I need to double. Okay, because I need to, when I'm giving you a new solution, I will have to ensure both of these conditions are satisfied.
One of the
So what's
eyes,
the one?
one of the eyes go inside, right?
Sorry?
One of the eyes go inside or one of the j's go inside?
So j is inside, right? And so imagine that some of these guys were inside, okay? Some were outside. Let's say 0.2, 0.2 and 1 was inside, and the rest was outside. Now I say that the rest of the guys are going to zero out. So now what is summation xij? It's only 0.1 plus 0.2 plus 0.2, only 0.5. But I want it to be 1. So I'm going to double these guys. So I'm going to say that, oh, this becomes 0.4, this becomes 0.4, this becomes 0.2. Now they add up to 1. I'm going to double them. I also have to double the yi's. Okay, so that's why I'm doubling this. So I'm losing some money here, right? I'm losing 2 in the approximation here. So far so good?
Are we doubling the yi's within the?
Yeah, but I'm flatly doing, doesn't matter. You're right, I should be more careful, but for me, I have no way of using that. Okay, good. So now you choose a j, right? Choose a demand with the smallest cj. Okay, smallest cj star value. So whatever this value was, you pick a j with the smallest one. Okay, so let's draw this. Right, so this is j and this has the smallest cj star and it is fractionally assigned in the new solution to various facilities. Right, so these are the i's to which it is assigned. Okay, so 0.1, 0.2 something, it adds up to 1 or more than 1. And now each of these facilities may be servicing more demands. Right, this could be some other j prime which is going here. Okay, so here's what I will do. Among these facilities, I'm going to open the cheapest one. Okay, so let's say this is the cheapest one. This I star is the cheapest. I open that. Okay, and all these guys here are going to go to I star. Okay, so this is where I will use the metric property. Okay, so all these j prime, so which are what? Which are neighbors of j and their neighbors. So all the demands which are assigned to one of the facilities to which j is assigned, all of them go to I star. I remove all of them. All of them go to I star, they are done, I remove them, then iterate. Iterate means what? Find another j which has the smallest cj value and do this, repeat the same thing. Okay, so you find some other j star or whatever, j double prime and again do this thing. Keep on doing this.
Could you explain the first step again?
Sorry?
Could you explain the first step again when I choose this j with the smallest cj star?
So I have not explained to you what was the motivation for picking but I'm giving you the algorithm here, the rounding algorithm, that you pick a j with the smallest cj. Why it's not clear right now, you will see why. Okay, now what do I do? All of these facilities here, how much does their yi's add up to? At least 1, because this guy is assigned to a fraction of 1 to these facilities, right? And these yi's will be at least xij. So these yi's add up to at least 1. So I pick the cheapest one. Okay, so I pick the cheapest one. And then all of the demands that you see, which are being assigned, partially assigned, right? I mean, 0.1, 0.2, whatever, they all go to this guy. Okay, and then I remove all of them, and then I repeat this. This is my algorithm.
All of the demands for which I star was in like the ball centered around J.
Well, I mean that I have already done, right? Good. So this is when I, in this X bar solution, yeah, which I did that part. Right? Otherwise, it could have been very far, right? So after I have done this modification, then I will go.
Okay, so I star was in J prime's ball too.
I star was in J's ball, right?
What about J prime?
J prime, no. So what does it mean? So J is partially assigned to several guys, right? These are in its ball, right? But look at each of these facilities. Look at the demands that are going there. All of those. And you will see why I am doing that. Why am I doing that? I am doing that because when you pick the next demand J prime and look at these facilities, what can you say about this set of facilities and this set of facilities? They are disjoint. They are disjoint. Why are they disjoint? Because if some facility I0 was here also and I0 was here also, then J double prime would have figured here, you should have removed J double prime. So these set of facilities and these set of facilities are disjoint. Okay? And yeah. So you are here for the rounding part is okay, right? Okay. So now I want to claim that okay, why are we doing this, right? So how will I pay for this thing? How will I pay for the cost of this facility? Well, the way I'm going to pay for this cost is that I'm going to say that the linear program puts some YI values here. Those YI values add up to at least 1. And so if I pick the cheapest one, its cost will be at most the total cost that the linear program pays here. Same thing here. But I have to make sure that no double counting happens. So this set of facilities here and this set of facilities here will be disjointed. Alright, so let's give it some names. So let's just call these cluster. So cluster 1, cluster 2 and so on. Okay?
How did you use the metric property here?
So for yeah, it's going to come. It's only going to come in the proof, right? So I'm not giving you, how bad or good this algorithm is. Now you will see. Good. Good. So at least we all understand the algorithm. Questions? Okay, good. So there are two things to bound. So let us bound the facility opening cost. Right, so how much did I pay in facility opening? So let's look at any of the clusters. So let's say in cluster 1, I paid the cheapest cost, right? So let's say I opened some facility I star, so I paid f of I star, right? And I want to claim that this is less than equal to, if you look at all these facilities in cluster 1, fi yi. Why is that? Because each of the FIs is at least FI star. Right? So let's just prove this. So this is at least sum over all I in cluster 1 Fi star yi. Correct? And then Fi star comes out. And what do I have? I have summation yi, which I know is at least. So this is true. And now when I add up over all the clusters, on the left hand side I will have the total facility opening cost. What do I have on the right hand side? Summation fi yi, because nobody is repeated. When you add it over all the clusters, no I appears in multiple of them. So that's where I am using the fact that there are no repetitions. Okay, they are disjoint. So my total facility opening cost is at most sum over all I fi yi. Okay? Where yi is the new solution, right, after I doubled and all that. Okay, good. Let's look at so far no use of the metric here, right? how much is a client or a demand paying? And this is where the metric will come in. Okay, so connection cost of a demand. Okay, so what do you think? How much is J paying? J will pay at most 2 Cj star, because by definition all of these are within 2 Cj star orbit, right? So J will pay, right? The center guy will always pay 2 Cj star. Okay, so again let's look at all the demands J. Suppose this was some other prime, right? J prime in cluster 1. How much is this guy going to pay? Well, do I have an upper bound on this length? How much is that? At most 2 Cj prime. Right? So this is at most 2 Cj prime. Sometimes putting stars, sometimes not. What about this guy? 2 Cj. What about this? 2 Cj. 2 Cj plus 2 Cj plus 2 Cj prime. Right? So at most 2 Cj plus 2 Cj plus 2 Cj. Okay? Which is less than or equal to 4. Now I use the fact, this is where the metric property is being used, triangle inequality, right? Because where did J prime go? J prime actually got assigned to I star, but that distance is less than or equal to this plus this plus this. Okay. So that's metric. And then I use that Cj was less than or equal to Cj prime, because I chose the J with the smallest Cj value. So this is at most 6 times Cj prime. Okay, so for every J prime, its connection cost is at most 6 times Cj prime. Okay, so connection cost, if you add up over all the demands, so this is not a very good approximation ratio, but at least I get a constant, right? So connection cost is less than or equal to sum over all J 6 times Cj. Okay. So what kind of approximation do I get? Here I had doubled the Ya, so this will be 2 here, but the dominating thing is this C6. So this is a 6 approximation. Okay. So you can do some balancing. Why did I pick a 2 Cj star? Should I have used 1.5 here? So you can do that kind of balancing, and you will see that you can get something about 3 point something, but you won't get better than that. Okay. So this is a constant approximation for percentage location, right? So and many papers that you will read, you will realize that this is a pattern they all follow. That you will pick a J with the smallest Cj or some other quantity like that, and then do this kind of thing. Now you can ask that will my optimal solution, will it ever do this kind of thing? Right? Will it really put some very tiny quantity on something very far? Because we are losing a factor 2 here. Okay, and so if I did not do that, I would have got a 3 approximation here. Okay, and turns out that for an optimal solution this will not really happen. Okay, how do you capture that? So the way you capture that fact is through duality. Okay, so I'm going to write down the dual of the linear program, do the same rounding for you, and just it will take 5 minutes, but you will see how you don't have to pay this extra 2 here. Okay, and then we'll come to primary. Okay. So what's the word?
You get like a per demand connection guarantee. It's not just a
Per demand connection. Yeah, so in that sense it's a strong. Although when I am picking the smallest J, I'm sort of amortizing over that. But yeah, you're right. It's fine.
You didn't have to pick the smallest J, right? All we need is that J should be smaller than every other J in the cluster. That's all.
Yeah, that's it. Okay, so let us spend some time thinking about the dual. So what is a dual? I will write down the dual for you. Maybe you know how to do this already, but I'll give you an intuition for what it is saying. Okay. But just to make things complete, how do you write down the dual? You have one variable for every constraint. So what are the constraints here? Here there are 2 kinds of constraints here. So this constraint is there for every for every demand j. And this constraint is for every pair of facilities and demands j. Okay, so I will have a dual variable. I'll have a dual variable which I will call, let's say beta ij here. Okay, and I'll call it alpha j here. Okay, and now I will write down the dual for you. But let us see what it's saying. Okay, so this is minimization. So that's a maximization. Okay, and because I have seen this so far many times, so I'll just write it down directly. But you can do this on your own. Okay, so it's saying something. You will see what it is saying. But I'm trying to maximize something. Okay. So I'll explain to you what this is saying. So think of alpha j as, every demand j. Think of it as the amount it's paying some money to get connected. Okay, so you're setting up all of this. Everybody is going to pay some money. So alpha j is right. So the intuition is that it's the money that j is paying. Okay. Now you don't want to maximize this, but there are some conditions. Condition is that the money that j pays, and let's say I is some facility. Okay. So j is some demand and I is some facility. Okay. Now money that j pays, some of it will get used for travel, Cij, right? This Cij. And the leftover, think of it as some sort of account that gets opened at I. So beta ij is some sort of extra account that will get opened at I. Okay, so the money I pay, Cij plus the extra account. And the constraint is that if you look at it, facility I, you add up all of these accounts that it is getting from all the clients, this will not exceed its opening cost. Okay. So essentially, everybody is trying to pay for a facility that is getting opened. How am I paying? I am paying for my own travel cost plus I am putting some extra money here for the facility that I am going to. Okay? But that extra money should not exceed the actual cost of the facility. And the question is, how much can I charge everyone? The more I charge, the better lower bound I get. Okay? So let's do this one more time. So just to understand this better, that we understand this slightly better, that you give me any solution, right? So any solution to facility location, right? So give me any solution has cost at least any solution to this. Okay, cost at least any solution to the two. Okay, so let's prove this. Okay, it follows by what you have seen, by how you write a linear programming dual. But let's see this one. Okay. So, but the interpretation you have to keep in mind is always that alpha j is some sort of money I am paying. Okay. So let's see this. Suppose you open some facility. Okay. Suppose there is some solution which opens these facilities. Okay. I1, I2, I3. And every demand goes to one of these facilities. Right. What is the cost of this facility? Fi1, Fi2, Fi3 plus their travel cost. And I want to prove that if you give me any solution here, its value cannot be more than that cost. And how will I prove this? I'll prove exactly according to what I just told you. So for example, if you look at a demand j here, how much is it paying? Cij. So let's add up their alpha values, right? Let's add up their total money that these guys have paid. Okay. Let us see how much money these guys have paid. Okay. Let's call this set D1. D1 are the demands which are going to I1. Okay. So how much money have they paid? Well, all of them have paid at most, right? So if you look at J in D1, each of them has paid at most, right, Cij plus beta ij. Right? So all of them have paid at most the travel cost to this facility, to I1, right, I1j and beta I1j. Okay? So they have all paid at most this plus some money here. So I break these two apart. So this is j in D1 Ci1j plus this extra bank, extra account that this guy has got, but that cannot exceed Fi plus Fi. Okay. So the total money these guys pay is at most the connection cost here plus the opening cost, and so this is same for everybody. So you add it up, then the total money everybody pays is at most the cost of the solution. Okay, so that says that if you give me any charging scheme, you're charging every customer some money, provided these two conditions are satisfied, then the total amount of money you collect from the customers, clients, will never exceed the cost of the solution that you're building. Okay, in that sense it is fair. Okay, but your goal is to now extract as much money as you can. The better you do it, the higher this will be. Now why do I want to extract as much money as I can? Because remember, so again this picture is useful. This is where your actual optimum was. This is where the LP optimum is, right? Remember we said that it is smaller. Where is the dual? Where is the optimum value of this guy? Well, okay, duality says that they will be equal, but in general, if you give me any solution here, we just showed that any solution to the dual will be less than any solution here. So this will be a solution to the dual, right? Okay? And duality theory says that these two will be equal. Okay? So what's good? Why do I care about LP duality? LP duality is because suppose I give you a solution to a linear program. How do I know that I'm close to the optimal solution? Right? Suppose I give you some solution here. How do I know that I'm close to this?
If you're close to dual, then
Yeah, because you will find also a dual solution and prove that these two are equal or close to each other. Then you must be very close to the optimal. So that's where people in optimization use duality a lot. Okay? So for us, what I will do is that if you give me a dual solution, I will find a solution here to the actual facility location problem where these two are close. Okay? And so that will be it. Okay. So suppose you give me an optimal solution here and an optimal solution here. Okay? Both of them are optimal solutions to the LP dual, right? Now the point is this. Do you know complementary slackness? Complementary slackness says that, what does it say? It says that if Xij is 0, okay, so what does it say? If Xij is positive, then what happens? Remember Xij, then this will be equal. Alpha j is equal to 0. In particular, this implies that alpha j is bigger than or equal to Cij. Okay? Which says the following, right? The thing that I was worried about earlier, that some demand j is fractionally assigned to somebody which is very, very far away. That's not going to happen. Why? Because if you are fractionally assigned to some facility I, the distance between you two is not going to be bigger than that much. Okay? So this phenomenon will not happen. Okay? So let me again give you the same rounding algorithm, but now with a slightly different twist. Okay? So first, everybody happy with me?
To put non-negativity in the dual as well.
Non-negativity follows, right? Yeah, sorry. Should I do? It doesn't follow that. You're right. So when you write down the dual, because these are inequalities, you will get non-negativity. Okay, so we have technique. So I'm going to show you one more algorithm. Okay. Was it too fast? Should I, so far, were you able to observe the rounding algorithm? So this is the second algorithm I am proposing. It's exactly going to look like the previous one. Okay. So now, but I'm not going to do that doubling in the filtering steps now. Okay. So what I'm going to do is I'm going to solve this for you. I'm also going to solve this for you. And remember, both of these quantities are less than equal to the optimal solution. Right? Right? Here is your opt. This is the linear programming opt. This is the dual optimal. Actually, this will coincide with this. Okay. So, all right. So now the algorithm is the following. Okay, so pick. So exactly same as before. The only change will be the choice of j. So pick a demand j with the smallest alpha j value. Okay. So this is the only change in the algorithm. Everything else remains the same. Okay. So pick a demand j for which this alpha j, the money it's paying, is the smallest. Okay, and then do exactly what you are doing. Okay. So all of these guys will go to. So what do? You open the cheapest facility here, right? So open the cheapest facility here. Okay, and then everybody gets assigned to the cheapest, just like before. Repeat exactly the same one. Only changes this. So now, what happens to the connection cost and the facility opening cost? Everything remains as before. Just like before, the facility opening cost is at most summation I by I, fi by I. Right. So facility opening cost, no change in the argument. Right. What about the connection cost? The connection cost is, let's look at this guy j prime. How much is this? This is less than equal to alpha j prime. This is less than equal to alpha j. This is less than equal to alpha j. So it becomes 3 times alpha j. Okay, so connection cost is okay. So I am going faster with this, but you can see where this is coming from, right? Same argument as before, but I don't use that factor to here. Okay. What do I get? I get this plus this, which gives you a 4, which is still not 3. But if you wanted a 3, you will have to make slight changes in this. I can get that as an exercise. So instead of picking the cheapest guy, you will pick a randomly chosen facility here. So you will get a 3 here. Okay. So, but this is the complete algorithm. Okay. So, okay, so that's a small thing, right? I mean, you can use duality sometimes to improve your algorithm. People understand? But what I wanted to get at, when you use dual, you can do something more with it, and perhaps you have already seen this kind of thing in vertex cover and set cover. That solving a linear program is an expensive thing. It's a time-consuming task, and if a problem is very large, then solving a large linear program will take a lot of time. Question is, do I have to solve a linear program? Can I run an algorithm which uses these ideas as a guiding tool, but which don't sort of explicitly solve a linear program? What are such algorithms called? We may not have seen. These are called Primal-dual algorithms. Okay. So what I will do now is, I will not assume that you're giving me an optimal solution here or here. Okay, so this is the third algorithm I'm showing you. This is, in some sense, the most efficient one, because it will not solve a linear program, but it will still build on these ideas that alpha j should be thought of as the amount that j is paying. Okay.
Dual, where did the metric property get used again?
Where? Here?
Yes. How does alpha j inherit the metric?
So right, I mean when j prime is getting assigned to here,
Yeah.
so this cost is this plus this plus this.
That's just by construction. Whereas like somehow the metric property isn't as explicit.
No, so metric property is used because why do you say construction? Because I mean j prime is, let's say, getting assigned to this point, right? And I want to upper bound the cost of this,
Yes.
the distance here.
Oh,
But this distance is at most this distance plus this is. So that's where the metric is. Okay? Okay. So what's the plan now? So for the remaining part of the lecture, the plan is to solve the same problem again. And you will see this problem has been studied so so much depth that more techniques are there. So when Professor Naveen Garg will talk tomorrow or day after tomorrow, he will teach some other techniques for solving facility location. So the idea is not to sort of look at what results we get for this particular problem as such, but to see the variety of techniques that people use here. So that's why this is, this has been such a fundamental problem. So what I will do now is I will forget about the primal law. I will give an algorithm which will build a dual solution. Okay. So again, that picture is very useful. I will give you an algorithm now which will give you a dual solution. Okay, it will build a dual solution, and it will also give you an integral solution for facility location, so that this thing and this thing are close to each other. Okay, so by default, u and opt will be close to each other. Okay, so now instead of using a black box solver to solve this LP, I will meticulously, use my own algorithm to give you a solution here. I will have more final level of control here. Okay, and this is something that you will,
An integral solution of the dual will be towards the left, right?
well, dual, I mean for that I care about an integral solution. For this I don't know what integral will mean. Right? So I'm not looking for an integral solution here. I won't have an integral. Yeah, but you're right. You don't like them. Absolutely. Yes, you're right. Which is okay, right? I'm comparing my solution with that. So whatever method I use, my strategy should be to extract as much money as I can. Because the higher this is, the easier will it be for to have a bound like this. Okay, so the goal is to get as much alpha j as possible. Okay, good. So this is called a Primal-dual algorithm. Okay, and as you are all saying that I want to raise money, right? I want to raise money, and the way this is going to work is that initially alpha j will be equal to 0 for everyone, and then everybody will start paying money. Okay, so I will, at a uniform rate, alpha j's will increase. They'll keep on increasing. Okay, and you will tell me what's the bottleneck, what stops them from being, raising forever. Okay, so the algorithm is very simple. It says that initialize alpha j to 0 for all j. Okay, and then so everybody money is 0, right? And now what I want to do is I want the demands to start raising alpha j. So I ask everybody to start paying at a uniform rate. That's clear. So at 1 minute of time, everybody pays 1. At 2 minutes of time, everybody would have paid 2, and so I'm getting more and more money. As time evolves, and everybody is paying more and more money. So by time t, everybody would have paid t amount of money. What stops this process? Why is it that I can't charge infinite amount of money to everyone?
Because of the first constraints alpha j.
Right. Now when alpha j at some point, right, so suppose this is some demand j, right, and suppose this is some facility I, and this is j to I, right, when alpha j exceeds Cij, and if I raise alpha j beyond that, then this is an issue. I can't do that. So what should I do? Should I say that don't start, or do I have any other lever? What can I do? Remember, I want to extract as much money. So one idea would be that the moment this happens, the moment alpha j becomes equal to Cij, you say that stop, you can't pay anymore. Right? Because otherwise if you raise this, then it's getting violated. But this is bad, right? This is bad because what if, for every j there was a facility nearby? Maybe this was a very expensive facility. So we will not open it. But ji is very small, so very soon alpha j will have to stop paying. Right? I wanted to get as much money as I can. So what can I do? I mean, there more. Think of that, right? There's another thing, right? Remember what was the interpretation? Alpha j is the money I'm paying, and there's another variable that I can control, beta ij. So what should I do? I say that okay, you can still raise your alpha j, but then if you have already reached Cij, so then as you're raising alpha j, you should also raise beta ij, so that this inequality does not get violated. Can this go on forever? Why?
Second constraint.
Yeah, at some point of time you will hit this barrier. At that time you have to absolutely stop. But that may be okay because by that time you would have paid for opening this facility. Right? So this is the overall algorithm. So let me write it down, and again somewhere we have to use metric property, as you will see. Okay? And I mean, one thing you have to understand that even though thinking of beta ij as the money that j is paying towards I, many of the beta, right, beta I1j and beta I2j both can be positive. Right? So it's possible that, for example, this is j, and this is I1, and this is I2. At some point, alpha reaches I1j. So when you raise alpha j, you have to raise this guy also. Similarly, when alpha j reaches I2j, you have to raise I2j also. So the same j could be paying for multiple facilities, right? That's possible, right? But then one has to be careful, right? Okay, you can only charge one demand. Each facility can, each demand can only eventually pay for one facility. But in the algorithm or in the fractional solution, many of these can be positive. Okay? Okay, so what is the algorithm? Let me write down the algorithm. I think I've explained the main ideas. So I'll write it down, and then we'll have questions. The actual analysis will not be difficult once you understand what the algorithm is. Okay, so initialize all the alpha j's to 0. Okay, so we shall say that j is tight with I. Okay, we shall say that j is tight with I if alpha j is bigger than or equal to Cij. Okay, in some sense, the moment alpha j has exceeded Cij, I'll say that you can't just raise alpha j. If you're going to raise alpha j, then beta ij. Okay, this is one notation. The other notation is that we shall say that facility I is frozen. Okay, not frozen is not the right word. They be paid for. Facility I is paid. Okay, facility I is paid if you have equality here. Okay, if summation j, if you look at how much everybody has contributed to me, it has reached. Okay. All right. So what's the algorithm now? So everybody raises alpha j at the same rate. Yeah, and some events can happen. Okay, so right, so everyone, right, so raise all alpha j at the same rate till one of these happen. Okay, so everybody is raising. What events can happen? Well, what could happen is that alpha j exceeds Cij. So if alpha j exceeds alpha, if j is tight with some I, then you should be raising beta ij also at the same rate. Right? So if j becomes tight with I, okay, then as you raise alpha j, you have to raise beta ij also.
So if like by using the complementary stepwise you show that xij is greater than 0, then alpha j is greater than equal to cij. So alpha j could not be
This condition, this is for optimal solution. So this, of course, I won't have anymore. This was there for the previous. I'll erase this. This is not relevant now. But this is something called complementary slackness condition. So if you have an optimal primal, optimal, I can discuss more about this later, right? But that's something you don't have to worry about now. Okay? So what can happen, right? What can stop me? If I raise alpha j, what would happen is that alpha j becomes equal to Cij. At this moment, as you raise alpha j, you have to raise beta ij also. So then you raise beta ij at the same rate also. Okay? Second thing which can happen is that, what else can happen? Well, what if this becomes equality here? Now the beta i's cannot be raised, right? Some I becomes paid for. So some facility I gets paid. What that means is that there is equality here. I cannot raise beta ij. So what should I do? Anybody who is tied with I cannot raise their alpha j's now. Right? That's not allowed. Why? Because if you are raising those alpha j's, you will have to raise beta ij, but beta ij is already frozen now. Right? So then freeze all the demands which are tied with that are tied with I. Okay? Can't raise them anymore. So you raise only the unfrozen ones. Right? The ones which are not frozen. Okay? So initially everybody is unfrozen. As time goes along, if your alpha j reaches some Cij, then you also have to raise beta ij. Beta ij's are, if they reach some Fi, you will stop. Note the curious thing, right? So suppose a facility I is paid, right? So suppose this I gets paid at some point, right? This equality holds now. And at this moment, this j is not tied with I. Now you keep raising alpha j, at some point of time this alpha j will be equal to Cij. The moment it touches it, it has to freeze. Right? So it will freeze at Cij. Okay? Because once this guy has been paid for, anybody who touches it cannot raise it anymore. Okay. So this process will eventually stop. Okay. So far so good. Now I can't, okay, so what is the solution now? Right? What are the facilities I'm going to open? Now I can't open all the paid facilities. And the reason is the following. I want to make sure that the facilities who are getting opened, the same demand has not paid for two of them. Because when I do my final accounting, I will have to charge some alpha j's. Right? I mean, alpha j is the only money I've got. So every open facility will say, okay, let me charge you guys. So two different facilities should not be charging the same demand. So I can't just say that whoever is paid, just open all of those guys. So I'll have to maintain some sort of disjointness there. And this will look very similar to the kind of clustering we did in the first algorithm. Okay? So let me then give you the final piece here. So far everybody with me?
when you stop, every demand has a tight facility associated with it.
Or maybe more than one. More than one, right? Why would it be more than one? Let's see why. Because yeah, that's a good point. So suppose this is J, right? And it becomes tight with this. It has become tight with this. Now alpha J is being raised. Both of them are being raised. At some point, maybe this gets paid. So J becomes frozen. And at a later point of that time, some other J is raising. So this also freezes. Right? So yeah, so it's possible that I am tied with two guys which are paid. It's possible. Okay, so what's the final algorithm? So so this is my this telling you how I am going to raise my money. And now whatever solution I build, its cost has to be comparable to the money I have raised here. This is all I've got. Okay. So so the final piece of the algorithm is saying question. So the final piece of the algorithm is which facilities to open. Okay. So let P be a set of paid facilities. Okay. So what I'll do is pick any paid facility here. Okay, so pick any paid facility I. Okay. Open it. Okay. Pick any paid pick any I in P. Yeah, I'm going to open this guy. Yeah.
Is it not true that all the I's will be get paid?
What will happen?
All the I will not get paid because
All the I's will not get paid.
we are increasing until beta is
Maybe suppose somebody's FI is infinity, it's super expensive, so that will never happen, right? Or maybe some guy is so far away, some facility, that you never become tied with that facilities. So all I's will not get paid. But when this process stops, every J will be tied with at least one paid facility. Because why did you stop raising the alpha J, right? Good. Okay. So pick any I in P and let's look at all the demands which are tied with it. So these are the demands which are tied with it. Okay. So it's again like the clustering step, you will see. Now these J will be tied with some other facilities in P. Okay, so they will be tied with some other paid facilities. So this I prime is in P as well. Okay, so this is clear. So again we are going 2 steps. So pick any facility I from your paid. Look at all the clients' demands which are tied with you, and they would be tied with some other guys in P as well. Remove all of them from P and repeat. So this is again trying to make sure that if I is going to charge J, nobody else is going to charge this, right? Because everybody else who could have charged J is gone.
Will there other I always exist or?
Other what?
So if some I is J and that is J and there is another I prime, so will that always exist or not?
They may or may not exist. So that, for example, let's look at this example here, right? So suppose this J is there, okay, and it is tied with 2 facilities. And at some point, both of them get paid, right? Why will both of them get paid? Because maybe there are other demands also, and they are raising this beta I, and similarly for this guy. So it's possible that a J is tied with several paid facilities. So that's what we are doing here. You pick any I and look at all the demands which are tied with me, but they could be tied with other paid facilities also, right? So I'm sort of removing those, right? I mean, if this is confusing, it's possible that although I'm drawing it like a tree, but I mean there could be intersections here, but whatever they are tied with. So far so good. and repeat this.
How do you read out like if there's a J prime who's tied with I prime?
So I don't care, it won't matter. Yeah, it won't matter. I don't say that pick the cheapest I in the P or something. It won't matter. Because eventually I'll be charging alpha J's and they are paying for it. Okay, right? So we'll see. Okay. So
It's all paid facilities that are like 2 hops away are removed.
So yeah. So let's look at so let's analyze this algorithm. Okay. So there are two kinds of facilities, right? One is this center facilities, and there are the non-center facilities. So what is the facility opening cost? Well, this Fi here, right? Remember, is equal to beta ij, right? So each Fi is equal to sum over beta ij over all j, which j's? Which are tied with it. J which are tied with it, right? J that are tied with it. Okay? And so if you do this summation, what do I get? Look at the sum over all the open facilities Fi. This will be sum over all beta ij, right? And there will be no overlap here. Why will there be no overlap? Because this j, whatever it is tied with, I have removed all those guys. Okay? Okay. So alright, so let's see. So total Fi, and let's say P prime is the set of facilities you open. Right, so P prime is a subset of P prime is the open lines. So this will be Fi is equal to sum over all j and sum over all I in P prime. Okay, and j is tied with I. Okay, and this is sum over less than equal to. Yeah. Okay. So let's keep it like this. Okay. What about the assignment cost? Any j. So if you are open and j is getting assigned to an open facility, this assignment cost is Cij. Right. So if j gets assigned to an open facility, right. So if j is tied with an open facility, with a facility I in P prime, then assignment cost is Cij. Right? What if you are not tied with an open facility? How much will I pay? Okay, and I would claim that. So this is where this will get interesting. So okay, so what if every client? What if j is not tied with an open facility? How much will that pay? Well, when the process stopped, every demand was tied with some facility. But now you are saying that the facility that I am open to did not get opened, which I am tied to did not get opened. What happened? Maybe I was tied to some guy here, right? So there was a demand which was tied to this guy, and that guy did not get opened. Why did it not get opened? Because this happened. Somebody else preceded me, right? And so this guy got opened, and so that sort of left me, unattached with anybody who's paid. Okay. So now I'm going to use triangle inequality again, And I'm going to say my ascending cost is this plus this plus this. Okay? And this I'm going to bound by something. Okay? So let's see. So when J became tied with a, everybody is tied with a paid facility. So let's say J was tied with some paid facility. Let's call it I prime. Okay? So everybody is tied with some paid facility. Okay, so J was tied with a paid facility. Right? So when alpha J froze, right? So when alpha J froze, it was tied with a paid facility. Okay, so this is J, and everybody is tied with the paid facility. So let's say I prime, J is tied with I prime. You did not open I prime. Why did you not open I prime? Because there was some other guy which is tied with I prime, which is also tied with some other I, and you opened that I. Okay? Now this is the time at which I prime got paid and you froze J. So till this point of time alpha J was being raised. And at that time you stopped raising alpha J. But this guy was also tied with I prime. When did this guy freeze? Only after this point. So whatever this, okay, so this is one argument you have to check. Let me call this J prime so that it's consistent with that notation here. J prime, J here. I claim that alpha J is at least alpha J prime. Okay? So convince yourself about this. So then this distance is at most alpha J plus alpha J prime plus right, I'm doing this the right way, right? Just one second. Yeah. Sorry, alpha J is less than alpha J. Why? Because when this freezes, this also freezes at that time. So alpha J, okay, you convince this. So this is at most 3 times alpha J prime. Okay? So if J is tied with P prime, it is Cij. If J prime is not tied with an open facility, this is at most 3 times alpha J prime. Okay, again, this argument, let me do this again. So J prime stops because I prime gets paid. Then at this time J will also stop. So either J had stopped already or it stops now. So alpha J is less than equal to alpha J. Okay, so then we are done, right? So let's put together everything. So what do I get? I get 3 alpha J prime there. You have this plus this here. This plus this will again be alpha J. So you will get 3 alpha J prime for those J prime which are not tied with an open facility, and you will get alpha J for those J which are tied with an open facility. Okay, so if you will do the total sum, maybe it's an exercise for you today, to just convince you that everything is okay, that if J is tied with P prime with an open facility, then you get beta ij plus Cij, and if J is not tied with a facility in P prime, this is 3 alpha J. So this is again equal to alpha J, so you get overall at most 3 over 3 times J. Okay, so that's the 3 approximation. Okay, so I went a bit fast, I know, but maybe as an exercise you should do this last part yourself. But I hope the algorithm was clear. Now, these are techniques which are useful for facility location problem, but maybe I can tell you more about what are the other variations people look at, because I have 3 more minutes. So there are many variations of facility location. This is the most basic one. The next one is called capacitated facility location. So capacitated means that every facility also comes with a capacity. So you cannot assign any number of demands to a facility. So every facility specifies that I have so much capacity. Okay. What happens then? Can you write a linear program again? Turns out that you can again write a linear program relaxation, but then this relaxation is very bad. Okay. It has an unbounded integrality gap. So either you write a better linear program, which people have done, or you use some other algorithm. So this linear program that I showed you, if you try to extend it, then it won't work. So that's capacitated facility location. Then there are other variations which are called, let's say, there are two parameters here. One is the facility opening cost, the other is connection cost, how much they travel. So in other formulations, people freeze one of these parameters. So they say that, for example, what is called a K-median problem. In K-median problem, they will say that, let me freeze how many facilities you are going to open. So I tell you that open K facilities, wherever you want to open. So there is no facility opening cost now. So open K facilities, and now you minimize the total distance that demands have to travel. And you can imagine, again, one can write a linear program for that, which will look very similar to what we have written. And again, you can write on a dual for that, which is very similar to how this looks like. And again, all of these ideas get used even there. Okay. Similarly, you can have other variations. You can have, for example, K-median problem, where you're opening exactly K facilities, but every facility also has a capacity. Okay. So capacitated K-median problem. So to this date, it's a big open problem, and we don't have a constant factor approximation for that. Okay. And then there are many other variations also. You can have some additional constraints that, for example, there's something called connected facility location, where you say that the facilities that you open, they should also be connected to each other. So you want to pay for the combined cost and all that. Okay. So there are many variations of facility location, but most algorithms that you will see will build on ideas like these. All right. So let's stop here.
Are there any questions? Seems like, okay, sorry.
The final Primal-dual is strongly polynomial. This raising we can do like.
So okay, so good. So this gives 3.
Yeah.
It is an open problem that this linear program, the actual answer should be 2. But we don't know. There are other algorithms which will give you almost 2. So now there is an algorithm which gives you 2 plus epsilon for any epsilon positive, but it's an extremely complicated algorithm. But as far as this linear program is concerned, people believe that it should be a true approximation.
Are there any methods to solve this problem other than?
Yes, other than linear program. So you will see a local search you will see next time. Actually, when you see Professor Navindar's lecture, probably he is going to talk about local search methods, and those will also work with the reason why people prefer LP is linear program is because you can throw in many other constraints, and it's just a very similar, very basic adaptation of these constraints. You can keep on adding more things to it. Whereas if you do local search or something else, it's very specific to a problem. You change the problem and everything changes around it.
Any other questions? Okay, if not, let's thank the speaker. Yeah, so coffee is outside. We'll meet back here in about 30 minutes.
Question regarding the runtime of this Primal-dual algorithm. See here, when you are saying like increase this alphas at a constant rate, now the number of iterations that you have to do, like it somehow depends upon this.
Actually, yeah, that's a very good question. But when you implement it, you don't implement it like this. You implement it as like, what is the next event that we have. So you don't run it in a continuous manner.
For example, rather than starting at alpha 0, you can directly go to CSS and then you can know.
Then you say what is the next, so that's how you do it.
So even then, like ifCij's and beta J's values are very large, then how?
No, but then how many events are possible? That either a J becomes static with some facility, some facility gets only these many events.